All right, guys. Nice to meet you. So today, Dr. Abdul Wasem will give you a guest lecture. So Dr. Wasem is the postdoc from Professor Jolin Lee's group. He has completed his Ph.D. in physics in South Korea. He has extensive experience in the epitaxial growth of gallium nitride nanostructures, such as firm and nanowires. On the application side, he has worked on LEDs, piezoelectric nanostructures, and water splitting. So today he will give you the guest lecture mainly about the epitaxial growth of compound semiconductors. So please give him a warm welcome about the hope you guys enjoy.
Okay, so he already introduced me. So today I am just giving a lecture on epitaxial growth of. So you hear me, because you hear me. Okay, that sounded fine.
Sorry.
In my lecture, I will briefly talk about the epitaxial growth techniques. So I believe you know basics about hydride vapor phase epitaxy, HVPE, MBE, CVD, and MOCVD. I will extend my discussion on MOCVD. I will talk about its gas delivery system, growth precursors, hydrides and amino sources, standard and dilution lines. So, did you know about dilution lines? Did you study about that? Okay. And then line configuration diagram. I will show that diagram here. Then I will talk about the epitaxial growth. I will start from the generalized concept about the epitaxial growth, and then what is the latest mismatch, how do we control this trend, and then growth optimization process, how do we optimize growth using our growth parameters, temperature, pressure, and flow, and then growth of gallium oxide, just a brief introduction. So you can ask me questions anytime. You can stop me. You can ask me questions. So in that way, I think that will be much easier for me also. So this is very brief introduction about HVPE. Most of the hydride vapor phase epitaxies, they have horizontal tube. Their sources, these are the precursors for gallium. Like they have pure metal source. Like you can imagine MBE. So in MBE you have crucible, you have pure metal, you just evaporate it with the E-beam. In this case, they control the temperature in these crucibles, and then they flow the gases. So for growth of gallium nitride and gallium oxide, they use HCl gas. So HCl gas flows exposed for gallium nitride. HCl gas passes through the gallium crucible. Okay, so gallium is in molten state. Its melting temperature is very low. So it just carries the gallium source from there, because HCl is acting as a carrier gas, and it just moves towards the quartz tube. In quartz tube, there are different temperature zones. So like low temperature zone, then the high temperature zone. At lower temperature zone, HCl reacts with gallium, it makes, you can see here the reaction, it makes GaCl. Okay? So GaCl is made at the lower temperature zone. When it moves to the higher temperature zone, so it splits. Okay? And like ammonia is used as the group 5 precursor. Like ammonia breaks into nitrogen radicals, and it reacts with gallium radicals, and it makes gallium nitride. This is for gallium nitride. And in case of gallium oxide, you can use the pure oxygen or N2O gas. Growth usually it happens at 700-800 degrees centigrade. Heater is actually wrapped around the quartz tube. So you have uniform temperature at the top side of the substrate, at the bottom side of the substrate. That is the plus point for HVPE. But problem is that the crystal grown by HVPE, they have a lot of defects, pits, surface pits. You can achieve very high growth rate, around 500 micron per hour. That is very, very high, highest growth rate. With MOCVD, you can achieve around 4 micron, 3 micron per hour for good crystal quality, if you just optimize the crystal quality. The grown layers with HVPE, they have very less strain because they are very thick. but their crystal quality is not good. So that is the drawback. The other epitaxial growth technique is MBE, molecular beam epitaxy. They have diffusion cells. So these diffusion cells, they are kind of crucibles filled with your metal source, and they are wrapped with the heater. As you can see, they are kind of heaters. So we heat them depending on the vapor pressure of your source, and we evaporate them. And here is your wafer, so you can deposit it. So it is ultra high vacuum system. It has advantages and disadvantages. High vacuum, you can grow crystals without defects, but growth rate is very low. Reason is that there are two precursors, group 3 precursors. When I talk about group 3 precursor for gallium nitride, group 3 precursor is gallium. Okay, so gallium is from group 3 in the periodic table, and group 5 precursor, it is nitrogen, ammonia, like whatever we use here. So issue is that suppose for gallium oxide growth, you need gallium source and oxygen source. So when the vacuum is very high, that means oxygen partial pressure is very low inside the reactor. So in that case, you create the oxygen vacancies, and the growth rate is very low. This is the more detailed schematic. So this is kind of window, you can see here the plasma. Okay. So these are the diffusion cells. This is the you can say there is a specific name. It is filled with liquid nitrogen just for cooling purpose. And the advantage of this EV is that it has reed setup. You can visualize your growth with this reed setup. This is E-gun. It's kind of XRD. You just strike your gun here. Here is your sample, and you can just see the temperature pattern from here. The other setup, you can see your flow rate of your evaporated samples. So the precursors, and here is the loading door, and here is the window. You can just see the plasma. As I mentioned, because of ultra high vacuum, it has low oxygen pressure. Specifically for gallium oxide growth, if I summarize it, so what happens? You oxidize gallium oxide, you oxidize gallium into Ga2O, and then Ga2O is oxidized to Ga2O3. Okay, so there are two steps. Because of low oxygen partial pressure, so you know about desorption and diffusion, out diffusion. So in that case, when you increase the temperature, when you increase the vacuum, so Ga2O is dissolved from the substrate. You want to grow gallium oxide, Ga2O3, but because of the low oxygen partial pressure, desorption rate is also high. That's why the growth rate is very low. So you have to tune your growth conditions to control the desorption, but still, because of the high vacuum, there is limitation. Researchers, they did some modification in NVE. Like they have investigated the catalytic growth with metal mediated NVE. Catalytic growth means whenever you use the metals, they act as a catalyst. Suppose gallium nitride is grown at 1000 degrees centigrade. So if you use the metal, you can reduce its temperature to 800 degrees centigrade. So metal is facilitating the growth. So that concept they use here. So they actually increase. In that case, they increase the growth rate because metal is acting as a catalyst, but still the growth rate, the maximum growth rate of fluid was around hundreds of nanometers per hour. Then they use the sub-oxide MOCVD growth mode. As I mentioned before, gallium oxide is grown in 3 steps. 2 steps, like gallium is oxidized in Ga2O, and then Ga2O is oxidized to gallium oxide. So Ga2O is a suboxide. So what they did, they are directly throwing Ga2O. So they are directly supplying Ga2O. Okay. So now they skip one step. So in that case, they achieve high growth rate, 1 micron per hour. But problem with this setup is that they cannot increase temperature above 550 degrees centigrade because If they increase, then resorption will happen again. So these are the limitations with MBE. So I think let's see one slide. Yeah. This slide should be top. Okay, so the other technique is the chemical vapor deposition. So what I discussed there are vapor deposition techniques. So in chemical vapor deposition, you are heating your sources. This is very conventional CVD. These are the sources. They have liquid sources, solid sources. So what they do, they flow the carrier gas through these sources. Any carrier gas in our case, M2, H2, argon. They are using argon and M2. So that carrier gas carry the source and then it delivers to the furnace. So this is furnace quartz tube. So this is the CV that I was talking. So they can achieve temperature up to 1100 degrees centigrade with this setup. This is also horizontal reactor. So the issues with the horizontal reactor, if you see there, yeah. So this is your substrate. Heater is in this panel and in this panel. They actually close it and then heater is right around the car slip. So when gas comes, there are different temperature zones. So it is very difficult to optimize the flow rate because each precursor has different density, different masses, different weight. So you have to tune your flow rate uniformly. The other issue is that their sources, they are solid sources, metal sources. Usually the metal organic sources, they must be heated because they have different vapor pressures. To evaporate them, we should give them heat. But in this system, there is no heating, so they wrap the heating cable around it, but it is still heated. So these are the limitations. When you increase the flow rate, let's say it will directly go to the output. You have to tune the flow rate. So why we move to the MOCVD, I will tell you in one slide. So MOCVD is actually metal organic CVD. It is CVD, but metal organic, we are using metal organic sources. So in MOCVD, I will talk about their source delivery system that is very advanced. Reaction chamber. Reaction chamber means what is the shape of reactor, and then standard dilution lines, and circuit line diagram means the line configuration. I will show you. This is the metal organic source. Okay. For different precursors, for gallium precursors, we have trimethyl gallium, triethyl gallium. This is a chiller and heater. We can control the temperature of the source because every source, like trimethyl gallium, trimethyl aluminum, trimethyl indium, they are different sources, so they have different vapor pressure. So to evaporate them, we need to heat them, we need to cool them. That's why we have this system here. The gases, carrier gas, it comes from here and then it carries the source and it goes outside. Then we have mass flow controller, MFC. We can control over SCCM flow, like 20 SCCM, 50 SCCM, whatever we need, we can control it from the software. Mass flow controller, gas can move in either direction. After the mass flow controller, we have electronic pressure controller. I did not have it in coming slide. I will show you. In electronic pressure controller, we can control the pressure. It has unidirectional flow. So these are the pneumatic valves. Pneumatic valves means suppose you have your carrier gas is nitrogen. You just carried your source, and this is the carrier gas. Okay, so let me explain you first the injection manifold. So gas comes inside, it carries the source, it goes outside, and then it moves either in the reactor side or to the exhaust, whatever we want. So we control the flow of gas to the reactor or to the baseline, to the exhaust using these injection manifolds. So these are kind of three-way valves. We can control them through the software. So do you have any question about this? Maybe I had a feeling that I could not explain it very well. So if you have questions, so I can just explain it in the best way.
I have a question. You said the gas flow insert.
Yeah.
So all of the gas flow insert from
Only the carrier gas.
carrier gas is the argon.
Argon, nitrogen, hydrogen. So it depends actually. Trimethyl indium, for trimethyl indium we cannot use hydrogen because hydrogen etches the indium, so we can use nitrogen. So depending on the metal organic source, we need to decide what kind of carrier gas we want to use.
Okay.
So mostly hydrogen, nitrogen, and argon they are used.
Okay, so I'm wondering what's the phase of your source? Is it starting or liquid?
Yeah. They are available. Solid sources are available. Liquid sources are available. The problem with the solid sources is that when you consume them, you know they are solid. Okay, so you are flowing gas. So when you consume them, suppose you have consumed 50%, then the flow ratio changes because it is consumed and you are not getting the similar flow as you are getting when it was new. So that's why it is discouraged to use the solid source. We have Epitaxial. We can see the concentration of source inside the carrier gas through this system. It is expensive. Most of the MCs they don't have Epitaxial. So the best way is that to get the solution liquid source. Problem with liquid source is that it, like for helium, it is trimethyl helium, so it has carbon inside. So it can give the carbon contamination. But nowadays the adduct production system it is really advanced, so there is no issue to use them. You can just heat it and you can get rid of contamination. Yeah.
Another question is, usually we need to use a hydrogen, but I didn't understand why we need to use a hydrogen.
Yeah, so hydrogen carrier, it is very nice carrier gas, and when you throw the hydrogen inside the reactor, so it increases the reactivity. Actually, it increases the temperature. Usually for reactor cleaning, if we want to clean them, so that is called high bay cleaning. We increase temperature about 1200 degrees centigrade and we just throw the hydrogen gas inside. So cleaning is very nice. It etches the impurities from the receptor. So in that way, the hydrogen gives you the high growth rate. That is inert gas actually. It is very difficult to break the inert gas. You need, in case of nitrogen, you need very high temperature to break it. It is around 1600 or 1900 degrees centigrade to break the nitrogen. But we have observed that when we use the hydrogen with the similar kind of growth conditions, hydrogen gives better morphology, gives better growth rate than the nitrogen.
I just said like sometimes we use a carrier gas at the argon or nitrogen,
Okay.
but sometimes we use X at the hydrogen.
Yeah.
We never use them both.
We never use them both.
Okay.
We can use them both in MOCVD. We have different MFCs and we can simultaneously use like 1:1 ratio, 1:2 ratio. So we can use carrier gas. So that in MOCVD there are two carrier gas. One carrier gas which is carrying the source from the bubbler to the reactor. The other carrier gas you are directly throwing the carrier gas from the top side of your shower head to just make the smooth delivery of precursor to the substrate. So that is not carrying the source. So this is confusion. So in conventional systems, the carrier gas is used hydrogen and nitrogen. We cannot use both of them to carry the source. So suppose you are using hydrogen for gallium. So you know each MFC they have different calibration factors. So suppose your MFC for hydrogen, you have MFC for specifically for hydrogen, and then you decided to use the nitrogen. Then you should have separate MFC for nitrogen because the calibration factor is different. So in that case, you will not get the exact flow you want. Yeah. So any other question for this? Yeah.
So the second horizontal line, like where you vent and exhaust the gas, Is the reason you have that because you use a
Yeah,
different
so let me explain you why do we have two lines. Suppose for the growth of for the growth of gallium nitride. So suppose this is sapphire, and then you have grown gallium nitride. Okay, then you want to grow GaN in GaN material quantum wells. Okay, or super lattices, whatever you want, very thin lattices around 10 nanometer thickness. So you are using PMGA, trimethyl gallium, as a gallium source. Okay, suppose for thin film your flow is around 70 SCCM. Okay, but when you go to the quantum well growth, you need to reduce this gallium and you need to introduce indium, that is GaN in GaN. So then when you will reduce it to suppose 20 SCCM, you have to because for the abrupt change of the gas you have to throw the remaining part in the baseline. So there is some differential pressure controller system makeup line. I do not want to go. Maybe their makeup lines are shown here. Yeah. So makeup lines, they control the supply the carry gas. So in case if there is some pressure difference inside the tubes, you can control with the makeup lines. So there is a base flow which is going to the vent side. So you can switch that flow to the reactor side just to control the change in the pressure. So that is very advanced system. So that's why we have injection manifolds. From injection manifolds, suddenly because we need the abrupt interface. So when we need the abrupt interface, we need to suddenly stop the carrier flow. Okay, so that's why we just in the software we just make the recipe and automatically injection manifold is switched from reactor to the vent side. So in that case we can get the abrupt interface. Okay, so any other question for this slide? Yeah.
Mine's just a quick one. So you mentioned there's electronic pressure controllers in addition to the MFCs.
Yeah.
Can you explain what the role of the pressure controllers are? Because
Yeah.
it seems to me like
I will explain in the coming slide. I have a schematic for that. And in that case you can understand better way. So here you can talk about the pneumatic valves. So pneumatic valves, there are two kinds of pneumatic valves, normally closed and normally open. Normally open means pneumatic valves, they are controlled with the compressed air. Nowadays they are using nitrogen also. So normally open pneumatic valves means they are always open if you have not supplied the compressed air. So when you supply the compressed air, they will be closed. So you can actually control them through your recipe. So this is the reactor for MOCVD. This is the vertical reactor. This is the susceptor. Susceptor meaning we just place our samples or substrate. So that is kind of substrate holder. So this top shower head, we call it shower head. Yeah, here. We call it shower head. So it has two plenum chambers. So upper plenum, we use it for group 3 precursors. For gallium nitride, like we can flow trimethyl gallium through this plenum. And the lower plenum, it is used for the group 5 precursors, depending on your compound semiconductor. So you can see here, these tubes, these holes actually, not these holes, they are very tiny holes. So these are the tubes. They are throwing your precursors inside the reactor. So these are the tubes. They don't mix inside the shower head. You cannot mix your group 5 and group 3 precursors inside the reactor. They will be mixed when they are flown outside. Then you are also flowing the vertical carrier gas just to speed up the flow to the substrate side. When your substrate is heated at different temperature, then reaction can happen. I will tell you how reaction happens in the coming slides. So this is only about the shower head. So there is a cooling system also. The water flows in this way. You can see here. The shower head has a cooling system, and this chamber also has a cooling system like their side walls. Then you have heaters here. So there are 3 heaters: center zone, middle zone, and outer zone. Zone A, B, and C. So these optical probes, they are used to just tune the to uniform, to make the heating uniform through all zones. Otherwise, your substrate at the inner side will have different morphology than the substrate at the outer side. So you have different separate 4 power supplies to control this heater, and then this is the exhaust which is connected to the vacuum pump. This is quartz aligner just to control, to make sure the heating is very uniform inside, and you know the reactor assembly. So this is very advanced reactor assembly. Yeah, so this is all about the shower head of MOCVD. And then so these are the precursors. Now we can talk about, as I mentioned, there are different precursors: aluminum, aluminum, TMG, TEG, TMIN, PEN, EZN, silicon. So these are the bubblers. This is the chiller that I had already shown you. This is MFC, and this is EPC, electronic pressure controller, and this is the Epitaxial. Epitaxial is used to control, to know the concentration of your source inside the carrier gas. We use gases, we call it high drive for NFC, for the gallium nitride, which is well known, and for gallium oxide we use pure oxygen, we use N2O, we use H2O. This pure oxygen, it is very reactive, but it is very nice morphology. You need to do very hard work just to control its flow and to prevent the premature gas phase reactions. Otherwise, what happens when you flow the oxygen, you flow your precursors, they react inside the gas phase before arriving the substrate, and they make the small crystals through the islands. So your film will not be uniform. So you have to flow the inert gas, you have to tune your pressure and temperature just to control it. I will talk about this. So N2O, recently few research groups, they have used N2O. It is also used as a dopant. It is really good precursor because it does not fully break inside the vapor phase, so you can have very nice morphology on the substrate. Carrier gases, as I mentioned before, N2, H2, and argon. H2 cannot be used for gallium oxide. Can never be used for gallium oxide because it reacts with oxygen and anything can happen. So that's why only N2 is used for gallium nitride and gallium oxide. Argon is used for gallium nitride and gallium oxide. H2O cannot use it. Yeah, so this is about the standard and dilution lines. First, I will talk about the gas. So why we need dilution lines? Standard lines mean you just directly flow your gas. Suppose you have N2 or H2. So these are normally closed valves. These are normally open valves. You can close them. You can open them depending on your need through the software. Okay. So these are the pneumatic valves. This is MFC. You can control your flow through the software. Suppose you have MFC, its maximum flow is 200 SCCM. Okay, so they have some error, like you cannot use the maximum flow. You should use 190, like 10% below the maximum flow or 10% above the minimum flow. Then it will give the uniform flow. So as I mentioned before, the injection manifold, we can control this injection manifold to switch our gas towards the reactor or towards the exhaust system. This is very simple. You just flow your gas whatever you need, and you can just get gas inside the reactor. Why do we need dilution? Because suppose for xylene, okay, so for xylene we need only few SCCM. I was using 1.5 SCCM, 2 SCCM. Okay. So in that case, you cannot directly flow 2 SCCM because in that case your flow will not be uniform. So you need to dilute it with the carrier gas. Yeah, we were using hydrogen for dilution. So you need to dilute it. So for dilution, you should have a dilution MFC, separate dilution MFC. You can flow, so there is a separate formula also. You can control whatever you want inside your reactor, how much. Actually, SCCM is not a standard unit. You should mention molar flow, okay, molar flow per minute. So Antoine's equation that is used to control the bubble pressure. So anyway, so suppose we flow group 5 mean we flow NH3 or for dopant. I will talk about dopant. So we flow SiH4 gas, xylene gas, and then we mix hydrogen inside it. So we have mixed for we need the total mixture is around 50 SCCM, but we need only 20 SCCM from that. Okay. So what we do, we will fix 20 SCCM at this MFC. The remaining will directly go to the baseline. Okay. That's why we have baseline before this MFC. So in this case, for dilution, we need 2 MFC. For standard line, we just need one MFC. We just flow the gas and it will go to the reactor. In this case, we need to mix the gas. We need to decide how much dilution gas do we need, and we need to do some calculation. And then, as I mentioned before, in GaN quantum wells, if you want to do, and xylene is used for N-type doping. Okay, for N-type doping, we use xylene gas. It contains Si, so Si is incorporated in gallium nitride and it acts as a N-type dopant. So if from these MFCs, so there are 2 output MFCs. It is not necessary our MOCVD only has 1 output MFC, but you can have 2 output MFCs. And why do we need 2 output MFCs? Just for the abrupt change, abrupt interface. Suppose in GaN you have 5 SCCM, but in GaN where you want less SCCM, what you will do? You will flow 5 SCCM here and 3 SCCM here. When you need 3 SCCM, you will use this one. When you need suddenly 5 SCCM, just close this one and use this one. Okay, so that's really abrupt change. So any question for this slide for dilution? Okay, so why do we need dilution? Because sometimes we need very less amount of precursor like xylene, then we need to dilute it with the other gas just to make uniform flow. Okay? So that's why we need the dilution. Then MO sources, standard and dilution sources. So this gap pressure controller is actually the EPC, electronic pressure controller. So here is, if I did not answer your question, you can ask me again here. This is Epitaxial. We don't have Epitaxial. So you flow your carry gas inside the bundle. It takes the it carries the source and it directly passes through the EPC, electronic pressure controller, and directly moves to the reactor or to the exhaust if you want it. Okay, you can control it. You cannot see here the base. This exhaust is different and baseline is different. Baseline is also connected to the exhaust, but baseline is only used when we have the dilution line. Okay, so don't mix the baseline with the exhaust. Baseline means you have diluted your source with the carrier gas, and the total flow is higher than your need. You can just throw the remaining source to the baseline. Okay. So this is the dilution, double dilution source line. In double dilution source line, you have one MFC, an input MFC here, and then you have an additional MFC just as the dilution line. You dilute it, you just carry your source and dilute it, and then throw it through the electronic pressure controller. Now, suppose you want 20 SCCM, but the total flow, the dilution is 40 SCCM or 30 SCCM. You will throw, automatically it will be thrown to the baseline. So where is the baseline? Yeah, here is the baseline. So you see here exhaust system, then waste sweep. So there are 2 exhausts here in case of dilution lines. Then suppose from 40 SCCM you need 20 is gone to the baseline, then 10, 20 is going to the reactor. Okay. So this is the purpose of the dilution line. Then this formula is used to calculate how much how much molar flow do you need inside the reactor, so you can control it through your recipe. Any question for this? So did I answer your question for electronic pressure control?
Yes.
Okay. So any other question for this slide specifically? So this is very important to understand if you work on MOCVD. If your dilution calculation is not good, you will grow, this will be grown, but your results will be very bad. So you need to do the calculation first before the experiment. There is another metering well. You can see in any line before the exhaust. And the role of metering well is that sometimes because of the makeup lines you are flowing your carrier gas. The company who gives you a MOCVD, they will always allow you, they will ask you to flow the higher carrier gas. Okay? But we can figure out a way to consume very low amount of carrier gas. So in that case, you can fix the metering well near to close value. You can just it is not digital well. You just rotate it. You can rotate it. So in that way, you can consume less amount of your carrier gas. So it is not going to the waistline. Okay? But if you block it, then what will happen? Your morphology will be different. Sometimes there will be a bad flow and you will not catch no flow. So don't block it. Just fix it to the near to the zero value. So I think I have explained. Yeah. So leak test means when you suppose you have installed new bubbler there, you have fixed it, and then you want to perform the leak test. Leak test means you just flow the gas and want to see if there is any leak. So for that you need very high vacuum, external vacuum pump, and you just use the helium gas. And if there is a leak, because this vacuum pump is sucking, if the helium is going to the point where is the leak, then the pressure of the vacuum pump will drop, and the vacuum will be dropped. So in that case, you will figure out there is a leak. So there is additional line with any source, with any line, there is additional line to connect to your vacuum pump just for the leak test. Yeah. Okay, and then this is the diagram. I think it is not clear, so I can show you a separate diagram. Yeah. Whatever I have explained, it is in this diagram. I have talked about the MO sources. So these are the MO sources, okay, metal organic sources. Wherever there are two MFCs, that means those are the double dilution lines. Okay, so we need double dilution lines for gallium, for aluminium. Yeah. Anyway, so this is TMGA 1, 2. Don't focus on these values. So what we do, we flow the gas. So here you can flow argon, you can flow nitrogen, you can flow hydrogen, whatever you want. You have your wells, you have your MFCs, and you can decide which gas should go inside the bubbler. Okay, through the recipe you can decide which gas should go. Like in case of triethylenium, you cannot use hydrogen, so we are just directly flowing nitrogen, or argon we can use. So then it goes inside, it carries the source, and then this is the, I just want to show you the waistline. In some cases, you see your line is connected here, your EPC is connected here, so that is the waistline. Okay. So in dilution lines, your EPC is connected with the waistline, but if the line is like this is dilution line, your EPC is connected with the waistline. Then this is the dilution line, and it is connected with the waistline. Okay. But for others, there are two injection manifolds, one for group 3 precursors, one for group 5 precursors. Okay, so these are for group 3 precursors, and these are for group 5 precursors. and I will not talk more about it. What I wanted to mention to you, I think I have already explained it. Okay, now just move to the crystal growth. Very fundamental. In crystal growth of nanostructure, a system. A system consists of two components. One is the medium, like in case of MOCVD, vapor phase. So above the substrate, your source is in the vapor form. Okay, so that is the vapor. Melt, there is actually another growth method that is our vapor liquid solid VLS growth mode. So I'm not talking about that. So let's talk about reason. Which supplies the system with the growth species. And the other one is the solid surface. Solid surface means your crystal which is grown, it is in the solid shape. Okay, so the vapor and solid, that is called VS growth, vapor solid growth. When the crystal grows from the vapor phase, the thermodynamics driving force for crystallization is expressed by the ratio S between the equilibrium vapor pressure of the supply. So that vapor is above the substrate, that is the vapor pressure that you are supplying, okay, and the pressure of the growth. So this S is called the supersaturation. So the density of precursors above the substrate should be higher. The chemical potential, I don't know you know about the chemical potential. So the chemical potential of the vapor phase should be higher than the solid surface. In that case, your crystal will be grown, otherwise desorption will happen. So yeah, I already have mentioned about this. Crystal growth can be divided into two major types of growth. The first is the growth of freestanding crystal where nucleation. So do you know about nucleation? Yeah, that is very fundamental. So on your substrate you should have some defects, some kinks, some calyces to initiate the growth. So that is the nucleation point. The second type is the growth of crystalline material on the surface of another crystal material or substrate. In that case, you need to study about the lattice mismatch. Okay, suppose you want to put a gallium nitride on sapphire substrate, so there is lattice mismatch of around 14-15%. Actually, it is 30%, but the crystal rotates and then ultimately it is around 15%. I will talk about epitaxy also in the coming slides. The process involved during epitaxial growth are shown here in this figure. So, suppose this is your vapor phase. You have high supply of your precursor. Chemical potential is very high. Your species, growth species, precursors, they are similar. Okay? So they are going towards the substrate. So either they will absorb or dissolve. Okay? Either they will attach to the substrate and will stop diffusion, or otherwise they can go. They can do desorption. They can out diffuse. Why this happens? Because if the density of your precursors is low, if the chemical potential of vapor phase is lower than the solid phase, then the desorption will happen. Okay? If chemical potential is higher, chemical potential of vapor phase is higher than the solid phase means this one, then your adsorption will happen. Okay? So you can tune it, you can control it with your growth conditions. The major growth conditions are temperature and pressure. Okay? By increasing the pressure, you can increase the density. By increasing the temperature, you can increase the migration of the air atoms on your substrate. Okay? So when you increase the temperature, their diffusion length is increased. This is the kink, maybe come the next. On the atomic scale, the crystal surfaces are not smooth, flat. I will talk about this. Surfaces of a crystal may be presented in this area. Every crystal does not have this shape. I just added it for your understanding. So there are several different kinds of effects. Okay, so your add atoms, when I talk about the add atoms, means your growth precursors on the substrate. Like you are using trimethyl gallium, its pyrolysis process is that it dissociates in dimethyl gallium, then monomethyl gallium. The activation energy of monomethyl gallium is very high. It directly goes on the substrate and it breaks during the diffusion process. Okay. Suppose it does not break during the diffusion process, then you will have the carbon contamination in your crystal. So these are the kinks, terraces, several kind of defects. So they are actually starting the nucleation. That's why to get the step flow growth means without 2D islands, very uniform thin film that has very uniform morphology. It is grown because of the step flow growth. So people clean the substrate before putting it inside the reactor. There is some chemical cleaning process. They can also clean the substrate at high temperature before growth starts. Then they can start the growth. The reason is that to just clean the surface and decrease the density of effects on the surface. So that is very fundamental. The process of nucleation can be understood with the help of this equation. J is the rate of formation of nucleus. This is the frequency of attachment of the molecules at the interface, and then gamma is the Zeldovich vector, depends on Gibbs free energy and the thermal energy. C is the concentration of growth species. So suppose this concentration is kind of equilibrium concentration, means vapor phase and solid phase, if the chemical potential is equal, that means the concentration in the vapor phase and on the substrate surface they are equal. In that case, supersaturation I will not go in details actually. Supersaturation means if your phase, whether it is liquid or vapor, it is highly saturated with the precursors. So if the chemical potential of vapor phase and solid phase, it is equal, in this condition the nuclei will not remain for the longer time because your temperature is also high, then desorption will take place. So in that case, if you know these tactics, you can control your, maybe one experiment will go wrong, and in another experiment you can just do your conditions and you can figure it out. You can grow your crystal. The condition for growth is that the nuclei that form during the process of nucleation should sustain unless growth is started, otherwise they will be good over. Then Gibbs free energy, every facet of the crystal has different Gibbs free energies. That's why are you aware about the crystallographic orientation of material? Like for gallium nitride, it has C axis, M axis, A axis, R planes. So every plane has different activation energy. Okay. So suppose sometimes growth is higher at one phase if you compare it to the other phase because of dangling joints and vacancies. So these are, if you go more in depth, then these are the things. Yeah. The optimization of concentration of growth species and Gibbs free energy, the growth along required phases can be achieved. So I think you have studied about it. So epitaxy, compressive and tensile strain. Suppose you have sapphire substrate, it is around 400 micron thick, okay, and you want to go around only few nanometers epitaxial layer. So that is epi layer. When you grow epitaxial layer on thin film, that is called epi layer. So they are in plane constant and out of plane constant. For hexagonal structure like in plane, biaxial plane AB and the C is the out of plane that is constant. So when you grow the epitaxial layer whose lattice constant is higher than the substrate lattice constant, in that case, suppose this is the substrate. Yeah. So these are the lattice constants. And you want to grow your crystal epi layer, but its lattice constant is higher. It starts from in this way. Okay. So what it will do? It will try to move in this way. Okay. So then in this case, the in-plane lattice constant, it is strained. The in-plane layer is strained, and out of plane layer it is just elongated. So this is compressed, this is out of plane layer is elongated. So this is called compressive strain. Here compressive strain means when your epi layer lattice constant is higher than the substrate constant. So here you can see this is longer than the in plane. This is compressive strain. When there is low compressive strain, it is very easy to do with crystal. There is no strain. When lattice constant is lower than the substrate, then you will have tensile strain. Okay. Your out of plane lattice constant will reduce, and in plane lattice constant will increase. In that case, you will have tensile strain. So this is very fundamental about epitaxy. If you are a grower, you will not get your. You know about homoepitaxy and heteroepitaxy. Okay? Homoepitaxy is possible for gallium oxide because gallium oxide substrate they are grown through the melt method and they are available at large scale. So you can grow gallium oxide. But if you want to grow gallium nitride on silicon, on sapphire, or aluminum nitride, so you have to deal with these things. So what people do, they introduce the buffer layers. So buffer layers mean maybe. Yeah. So this is aluminum nitride and this is gallium nitride. So you know Dr. Shuji Nakamura, he is Nobel laureate. He got Nobel Prize because of the blue LEDs. His work is very nice. But he was the first to introduce the gallium nitride buffer layer on the sapphire. The crystals, previously the crystals was grown using the aluminum nitride buffer layer or even without buffer layer. So their crystal quality was not good because of the lattice thickness. Then they use the buffer layer. Buffer layer means they have grown very few nanometer thick layer, maybe around 20-30 nanometer at lower temperature. So that is low temperature buffer layer. That is kind of amorphous layer. So then they reduce the pressure, increase the temperature. Then they go the high temperature. In that case, this buffer layer compensates the strain. Not fully, but crystal quality was much improved. So when we increased the thickness up to 3 micron, 4 micron, the crystal quality was very nice, even LED work. His other work was the MG activation, magnesium activation. We just activated it, you know about it. And if MG is not activated, problem with MG is that it reacts with hydrogen and makes the MG bond, which is neutral. So we need to activate it at high temperature. That's why we will have high density of holes and electrons when they combine they just multiply. I think that is out of topic. Kinetics, to understand crystal growth, we have to understand. Now here I am just talking about how we can tune the growth conditions. Okay? How can we, even with ALD, with sputtering, with CVD, with any technique, if you know these things, you can control your morphology, you can control your strength. The fundamentals are absorption, desorption, surface diffusion, effect of major growth parameters. I have talked about these three things. The major growth parameters are temperature, pressure. Yeah, these are important. So if we just tune, then 5:3 ratio, 3:5 ratio, we put 3 precursors flow and put 5 precursors flow. The ratio, it matters. Ratio means if you increase the gallium flow, what will happen? If you increase the nitrogen flow, what will happen? So maybe we can discuss it here. This is very I will try to summarize here. How can we tune the most effective growth parameter in crystal growth with the temperature, pressure, and 3:5 ratio or 5:6 ratio, because 3:6 ratio. 3:5 is for 3 nitrides, gallium nitride, and in GaN whatever. And 3:6 is for the oxide, gallium oxide, because oxide is from group 6. Okay. If the temperature, what will happen if temperature is too high? The desorption will take place. Okay, the air atoms will dissolve from the substrate, and then they run the bonds and nitrogen vacancies. In case of gallium nitride, in case of gallium oxide, you will get the oxygen vacancies. If temperature is too low, impurities, because you are using metal organic precursors, they have carbon, there are other impurities inside the reactor because you are using it again and again and again, so they lead to memory effect, and those are the impurities. That's why we have high electron concentration in undoped gallium nitride because of the impurities and defects. low surface mobility because temperature is low, diffusion length is reduced, and then ultimately you will get defects. So temperature is very not too high. If you increase, your growth rate will decrease. If you reduce, then you will just suffer from these problems. So you have to optimize it with your segments. If this ratio is high, that means your gallium flow is very high. Okay, so if gallium flow is high, that means you have more gallium on the substrate. So in that case, their diffusion is reduced because we are just striking with each other and they can create the 2D islands. Once 2D island is created, it will just start the growth of defect. So you will get defects in your crystal. If it is too low, then you will get imaginary vacancies and that will go down. So yeah, this was summary. I did not ask you any questions. So if you have any questions, just stop me and ask me. I don't feel like anybody will tell you about these things because I practically I deal with them. So these are really nice if you work on your part. I remove this slide. This is very generalized slide. So we shall have here people say this is expected and then suppose your sample is there, so you get this and I think this is not important. I will talk about it later. Gallium oxide crystallographic planes. So planes mean it is very important. If you are dealing with gallium oxide, this discussion is very important. You get these ribbons, these ignore from melt, then you get your substrates. What they do, they just cleave it. So there are different cleavage planes. It is very for gallium oxide. It is very easy to produce these substrates because they follow the cleavage plane, so they doesn't break. Even polishing is not needed sometimes. It is very hard to get these substrates. So these planes, I just added this structure for you. 100 plane, it is this plane. 001 plane, it is this plane, and then this is the 2-1. These are the cleavage planes. So 0, 1, 0, it is like this plane. It is the non-cleavage plane. So why I'm discussing it? Because your growth is different on each plane. Growth along cleavage plane, the epitaxial layers grown on cleavage plane, they are highly susceptible to drill boundaries and stacking faults. The reason is that you know about terraces, okay? You know about kings. Suppose this is the terrace width, okay? This is the step height, edge height. If you there is one way to grow good crystal on the cleavage planes. Only this is the way. If you don't follow this way, you cannot grow very nice film on the gallium oxide. This is miscut presentation. What they do, they have the substrate and they cut it at a different angle. Okay. So when they cut it at a different angle, in this way they can get very similar kind of terrace width and step height. Okay. So formation of 2D islands was suppose there the surface diffusion and terrace width, there is a very strong relation. If terrace width is very high, you have fixed your growth value. The other way is that you can tune your growth parameters and you can get similar way. Suppose you have fixed your growth parameters, then if your terrace width is higher than surface diffusion, you will get 2D island growth. 2D island means like this. They have not arrived at the edge side and it is grown here. Now it stopped the diffusion of other areas, and so you see here is the vacancy. So then in this case you will not get the uniform fill. So you have to increase your surface diffusion than the terrace width. In this way you will get the step flow growth. I have talked about the step flow growth. Okay, so in step flow growth means you have to reduce the terrace width and increase the surface diffusion. So when they cut the substrate at different angle, that means they are changing the terrace width. Okay. Then you are well aware about the monolayers and bilayers. Okay. If your substrate has mixture of monolayers and bilayers, that means your crystal will not be grown in a good morphology. You can grow, but morphology is very bad. So they cut it at different angles along specific direction. Suppose they cut it along 2 by 1 direction. Okay, so 0, 1, 1, 0, 0. Talk about this one. 1, 0, 0 frame is cut along this direction, then you will have very uniform. The wavelength of red color is long. So you have your substrate. You have very uniform. These are the terraces. You do have uniform terraces and monolayers. You can control the bilayer and monolayer, but your crystal will grow. The quality will be better if you have the monolayers. Only one layer, few atomic angstrom level height. So if you fix it, in that case your crystal quality will be good. Otherwise, bilayer mixture means this step height is higher than this one. That means this is the bilayer, this is the monolayer. So in that case, you will get the non-uniform growth. So what they do when they cut the substrate at a different angle, they are actually controlling the step heights and terraces. Yeah, I just added this one. I think this should not be here. Any question for this slide? Sometimes your explanation is weird, but we can explain better if you have questions. Yeah.
You might not know the answer to this question. How do they know what phase, like what plane they're actually cutting along?
Yeah, the crystallographic planes, they are well studied, well investigated, and when they have ribbon that I have shown you, so they know in which direction when they will cut, they will get this kind of substrate. To be honest, I don't know exact what kind of instrument they use to investigate the step height, and definitely some kind of optical characterization they do. But I'm not sure about it, about the name of that one. But it is well investigated, and it is very easy to get the missed cut orientation. There are a lot of commercial vendors, they provide the missed cut oriented. Even you can ask them to cut it along 2 degree, 4 degree, 6 degree. So it is possible. So there are two groups they have investigated that the better morphology was achieved when the substrate was missed cut oriented at 6 degree along 2 or 1 direction. Here I am talking just about if you don't know about the in which direction it should be off oriented, then you will have problems when you will grow the crystal. So your plane should be off oriented along this plane, not along this direction. Because if you cut it along 001 direction, you will get the mixture of bilayers and monolayers, so you will have different step heights. But if you cut it along 002 bar direction, I think messed up here. So if you cut it along this direction, then you will get very uniform step height and terrace width. So in that case, you can grow your crystal on cleavage planes. Otherwise, you cannot grow on cleavage planes. So these are their results. This cut orientation switching. So this graph is important, I think. So this is the missed-cut angle, and this is the terrace width. So you should know that when you increase the terrace, when you increase the missed-cut angle, you are reducing the terrace width. So that means that's why the morphology was very good at 6 degree, because your terrace width is lower than the surface diffusion. So in that case, your morphology is good. As I shown you, if terrace width is higher than the surface diffusion, morphology is very bad. So, but the problem was that the growth rate was lower, at the 6 degree. Then they optimize the growth conditions, and ultimately at 3 degree, 4 degree, they got around 3 to 5 micron per hour, and they got very nice crystal quality. So they worked it for several years, then they formed this solution. If they want to use the cleavage plane, but if you want to use the non-cleavage plane 010, as I mentioned before, it is very easy to get the cleavage plane gallium oxide substrates, because it is easy to cut them along that plane. Non-cleavage plane, The synthesis is difficult. Several substrates break, sometimes they need the polishing also. But growth is really good on the non-cleavage layer. Every time you will get the step flow growth. Yeah, so this is the different. This graph tells about the growth rate with MOCVD. If we specifically talk about the gallium oxide, the maximum growth rate, it is above 10 micron per hour, but the crystal quality was very bad. So the good crystal quality and acceptable growth rate was around 4 micron per hour. 4 micron per hour. So if you increase the growth rate, there is a trade-off. If you increase the growth rate, your quality will be great. So you have to sacrifice somewhere. So that is the challenge. So these are the full width maximum. You can see there different growth rates, and this source is DPN. This source is solid source for gallium. It is not used now. The problem was that, as I mentioned before, you have one heater to heat the bubbler to heat your MO source. For gallium, we usually keep it at 5 degree. You can even keep it at 22 temperature. You can keep it and you can control your pressure, bubbler pressure. But for this source, you need to heat it above 100 degrees centigrade. And it is really challenging. You need to wrap up your whole line to the reactor, and if your temperature is not achieved, then it will be blocked because of sublimation issues, condensation issues. So it is not used now. Gallium, it gives higher growth rate at 850, but when you increase the growth temperature, the growth rate reduces. Okay. Gallium, it gives kind of uniform at different temperatures, from 850 to 950 degrees centigrade. So mostly now people they are using gallium. The vapor pressure of gallium, it is around 50 times higher than gallium. So when vapor pressure of bubbler is higher, that means you can get high growth rate. Okay. So vapor pressure is related to the growth rate also. So that's why this source is good. This is my last slide. So if you have any question there, you can ask me.
So what you just said about the trimethyl versus triethyl, with triethyl having a larger vapor pressure.
Yeah.
Why are the ligands that are on these metal complex, like on these metals, why do they not why couldn't we use something like methanol, like trimethanol gallium, where you have like the OH?
Yeah. As I mentioned before, the adduct purification process. So adduct purification process, previously they were using one ether electrolyte that was giving very high contamination. So after several investigations, several experiments, they have concluded that this 5-methyl gallium, it is best. Why it is best? Because to dissociate your precursors, it matters. When it comes through the shower head, it has very short time to arrive the substrate. So it must dissociate in the vapor phase. If it doesn't dissociate, it can go to the exhaust, or it can just create defects on your substrate, like impurities. So trimethyl gallium, it is well studied. If we compare trimethyl gallium with triethyl gallium gives higher carbon contamination because its dissociation is, maybe here you can see, yeah, it goes to trimethyl gallium than monomethyl gallium. Monomethyl gallium has higher dissociation temperature, it does not break, and sometimes it has carbon. Monomethyl gallium has carbon. Sometimes it penetrates into a crystal, so you have carbon contamination. But for triethyl gallium, its dissociation is two-step dissociation. It breaks in 2 steps, not in 3 steps, and it produces the very stable radical that does not contaminate your substrate. It directly goes to the exhaust. So that's why triethyl gallium gives low carbon contamination. The problem is that its vapor pressure is very low. Maybe yeah. So you see, this is 238 at room temperature, 298, and this is 4.79. is very low, and you need a bigger MFC mass flow controller for this one, because you need to increase its. We can increase its bubble pressure by heating it at high temperature, and we can also control the bubble pressure with electronic pressure controller. But still, even whatever we do, it will give the lower growth rate. Because 238 it is very high than diagonal. So that is the case where it gives the lower growth rate. But crystal quality is better. Then there are other things also, like triethyl gallium. It breaks in the vapor phase. That means its gallium radical, it is very reactive, and when it mixes with oxygen is also very reactive. So it makes crystal before aligning the substrate. So that can create defect in your substrate. Triethyl gallium, it is not giving very active gallium radical in the vapor phase. It will move to the substrate, and then oxygen can go and they can just make it oxide. So we need to. That's why we need to think about fundamentals. If you don't know the fundamentals, you will have problems. Okay, so I just move to my last slide. Yeah, so I just added this for gallium nitride because I talked about gallium oxide. I'm supposed to work on gallium oxide. So my experience is actually on gallium nitride. So this is an NH3 source. It breaks. The dissociation temperature for nitrogen ammonia, it is around 600 degrees centigrade. So you can break it. You can make the very active radicals, nitrogen radicals from NH3 from 600 degrees centigrade. Our growth for gallium nitride happens at 1000 degrees centigrade. See, conceptually, this schematic is not accurate. I just added it for your understanding. The setting is not in this way. The epitaxial setting is different. So this is very generalized schematic for your understanding. So what happens actually, you have substrate, you grow the epitaxial layer, so your radicals, this one and this one, they are moving to the substrate. During diffusion, they react and they make the iron crystals there, epilayer growth. So it is on you how you tune your growth parameters to make the uniform epilayer. Yeah. But to deal with the strain, you need to introduce the buffer layers, or you need to decide your best substrate which has very best lattice parameter, lattice mismatch. Yeah. Thank you. So, any question? If you have questions, so I think 4:20. So you can send me emails. I should have mentioned the email here. So yes, this is my email. So you can send me email about growth or epitaxial. I will be happy to answer you. So questions?
I didn't want to read paper. I read this a lot, but I didn't understand.
Yeah. It's a kind of activation energy actually. You should understand activation energy first. Activation energy of each facet. So when I talk about facets, mean C axis, M axis, or A axis. So if we go in detail, so activation energy depends on the density of dangling bonds. So do you know about dangling bonds? Like gallium should have nitrogen, but there is no nitrogen, so there is no bond. So it increases the reactivity. You just keep these things in your mind, chemical potential and activation energy. In this way, if you search it, then you can get very, very nice results.
So I just can simply think it's a chemical reaction.
Yeah, reactivity, chemical reactivity at the interfaces. So activation energy, as I mentioned before, you are using catalyst, right? So do you know about phase diagram? When you mix two metals, so there is eutectic temperature. That means suppose that melting temperature of age unit is above 1000 degrees centigrade. You want to reduce its melting temperature, what you will do, you will mix it with some other metal. So the detected temperature is reduced. So when we use the metal on crystal, so we are increasing the activation energy. We are increasing the reactivity. So in chemistry, in physics, different terms are used. Even conduction band, valence band, we use in physics, but in chemistry, different ways. So these are different terminologies, but fundamental is that how you increase the activation energy to start the relation of these two.
About the current space and the diffusion
Yeah.
surface.
So
I want to know what's the surface.
yeah. So fusion is, let's suppose this is this marker here.
No, I mean is a reactor's diffuse or is
The fusion of your add atoms. Add atoms mean your helium atom. Maybe you try more than helium. It when it strikes the substrate, it moves. Its diffusion, how long it moves in per second, that is the diffusion length. Okay. So you can increase your diffusion length by increasing the temperature. When you increase the temperature, your particles move in faster way.
So like I introduced the carrier gas and the carrier of reactor atoms. So you mean when the atoms doubling on my substrate, it will diffuse.
They will diffuse to the defect to the nucleation site. That's why I did not mention about growth methods. So there is one method, selective area growth. Selective area growth means you have selected this area, you want your growth only at this area, not anywhere else. So what you do is you deposit some materials for SiO2 for giving nitride. So it has very smooth surface. So your add atom, they are not initiating growth anywhere on SiO2. They will migrate to this selected area. When they will go there, they will nucleation will start. So ultimately, you are just controlling your diffusion.
So when I read paper, I say that if I increase the temperature, they will get the larger doping size. That is mean that the higher temperature increase the diffusion rate. It's easier to get the larger doping size.
Yeah. It depends on material to material also. Several materials have different activation energies, but the basic concept is that you have to change your diffusion of the atom on the substrate.
Maybe it's not related about it, but it's related about the growth. So actually why in my growth I always make the issue that I always get the bigger growth by very small domains. My aim is to get the lateral growth, the same layer.
So you are getting the 3D growth of the 2D layers.
Yeah, I won't get the 2D layer, but usually it's get very thick. So I guess the problem is I didn't introduce the enough dichitogen. Dichitogen, I mean the cellulite. I grow the monoacylide. So I didn't introduce enough cellulite. But I don't know how to increase the ratio.
Are you using some furnace?
Yeah, I use it. And that's the furnace you in the CVD picture. I usually use that one.
There are different things between MOCVD. We flow the carry gas vertically to increase the diffusion. In your furnace, if you increase the carry flow, they will just pass your substrate and not strike on your substrate. So what people do, I have studied several things. They tilt the sample. In this case, suppose this is the input flow. So when they tilt the sample, then they strike the source is striking the sample. So you have to strike. That can be a way just to test it. But in your case, pressure should be lower, flow should be lower. Not too much lower, it should be optimized between high and low flow. But low flow will give you higher flow rate. Higher flow will give you lower flow in your case. Then if you fix if you think about the pressure parameters, but if you think about the temperature parameter, that is correct. If you get the temperature, that means your diffusion that is increased. So there should be a growth rate. So bad morphology, good morphology, so you have to play conditions. Good crystal quality.
Yeah.
Okay. Okay, then thank you for your time. Thank you.
I'll be leaving my line.